Okay, lecture 2 on chapter 17. Now, where did we leave things? We left at the fundamental theorem of statistics. And what does this say? It says that even if a population is not normal, so let's take if population distribution not normal, so it's skewed or bimodal or whatever, like if it were categorical data. Categorical data definitely does not have a normal shape. Okay, it's all zeros and ones or yeses and nos or whatever. It's just basically two modes. Okay, if the population distribution is not normal and even if, let's say even if population is not normal, and here, let's do this. If n, the sample size big enough, then the distribution I don't know why this thing doesn't like to write ones. My eyes keep disappearing. Then the distribution of sample, let me try writing like this, statistics, and in parentheses I'm going to put p hat, which is the sample statistic taken from a proportion, or y bar, which is a sample statistic that is a mean. If n is big enough, then the distribution of these sample statistics is approximately normal. And that distribution for proportions, for samples taken from a population described with a proportion, the mean of p hat equals p, the population proportion, and the standard deviation for p hat equals the square root of pq over n. And for this, a sample in which described by a mean, the population parameter is a mean. Now for means, the population parameter is mu. Okay. The mean for y bar equals mu, if you know it. And the standard, we'll talk about this in a minute, but we may as well, the standard deviation for y bar equals sigma, standard deviation of the population, divided by the square root of n. So similar, very similar. All right, now, so we're going to make some distinctions here, okay? The central limit theorem, the mean of a random sample is a random variable. Okay, you know what a random variable is? A variable that can hold any number of different values. Now we're used to a random variable being held for a specific, like a discrete random variable or whatever, or a continuous random variable. It's a specific number for a specific factor. But now we are saying that y hat, that p hat or y bar are also discrete random variables. That is, they're always going to have a different value. And the distribution of these can be approximated by the normal model. And the larger the sample, the better the approximation will be. Up until a point, and then after a while, it doesn't matter how big the sample is. All right, so now we're continuing the conversation about means. Okay. Now, assumptions and conditions. If you're going to use the normal model, then your sample has got to be representative of the population. It must be random and independent. It can't be too big. The 10% rule still applies, okay? But we don't have, unfortunately, the way we have with categorical data when we're dealing with proportions, we have this nice rule. NP and NQ have both got to be greater than 10, greater than or equal to 10. That's such a nice, easy rule to use. We do not have such a rule for quantitative data. But we can say this: the more normal the distribution of the population, the smaller the sample can be. So if the population is really normal, like for what we're measuring, let's say weights of 18-year-old white U.S. males or something like this, something very, very highly specified, qualified population, will probably have a fairly normal distribution as long as we're talking about something like physical characteristics. Anything involving human behavior or something like that will never have a normal distribution. But anyway, if the population is normally distributed to begin with, then the sample size can be small. But if the population is not normal, like incomes, say, then or number of cigarettes smoked per person or something like that, it's not going to have a normal distribution. Then a large sample is required. Now, what's large? Well, that can depend. It's going to depend on how badly skewed the population is to begin with. Generally, for quantitative data, we stop worrying about sample size after 40. But there will be exceptions to that, I'm sure. All right. So we already talked about this. Here's the standard deviation for the sample statistic, Y bar, taken from a sample that for quantitative data. It's the standard deviation of the population divided by the square root of n. Notice that with proportions, we can create both the mean and the standard deviation out of the single population parameter p, right? So it's p comma square root of pq over n. Well, of course we got to know n, but we always know n. So, I mean, n's part of the sample. And q is 1 minus p. So if we know p, then we can generate the mean and the standard deviation for the sampling distribution. This is for p hat. But for y bar, we need to know both mu and the standard deviation. That has to be computed separately, as you know how it's done, divided by the square root of n. So that will present a problem later on that we will talk about. Okay, let's on to the next page. And here's more on the sampling distribution. Now, no matter what population the random sample comes from, the shape of the sampling distribution, that is the distribution of the sample statistics, in this case we're talking about the y bars, is approximately normal as long as the sample size is large enough. The larger the sample used, the more closely the normal model approximates the sampling distribution for the mean. All right. Now here's a bunch of math that you can study if you wish or not. I'm not going to go into it right now. So we have two closely related sampling distributions that we can use when the appropriate assumptions and conditions are met: random and independent, not too big, not too small. Which one we use depends on the kind of data we have. Okay, and here's it all put together for you. Categorical data. We have the true proportion, the population parameter, denoted by the Greek letter little p. In this book, other books use the Greek letter pi. But these authors thought that would be confusing. As a standard deviation for p hat square root of pq over n. Okay. And for means, the mean is simply mu, and then standard deviation is sigma over the square root of n. Okay, now this stuff, these formulas are provided for you on the test, and when I test you, you will definitely have access to them. All right, on to the next page. We got a recap here. All right, we're going to talk some more about these women with the 200 female students who self-reporting. Now this time, they're reporting on weights. So before we had the proportion of women whose BMI was 25 or greater. Okay, now we're going to talk about their weight. So now we're talking about quantitative data. So the CDC says the mean weight of 18-year-old women is 143.74 with a standard deviation. So here are population parameters, two of them. Mu equals 143.74, and sigma, another population parameter, Greek letter, equals 51.54, and these are both pounds, lbs. Okay, now we got n equals 200. Okay. All right. Now, the mean weight of these 200 women, Y bar, equals 140. Okay, does the mean weight in this sample seem exceptionally low, or might this just be random sample-to-sample variation, something that we could expect to occur randomly, assuming that this is true? Okay? All right, and we got to go through the preconditions, and you got to say them. Now, they tell us that this was a random sample, but you must say that it's a random sample. Okay? And you have to state that this is less than 10%, 200 less than 10% of all women at the college. And large enough. Okay, watch this and listen, because you're going to have to reproduce this. The distribution of college women's weights is likely to be unimodal and reasonably symmetric. So the central limit theorem applies to means of even small samples. 200 values is plenty. Okay? So you want to take that in. Because this kind of thinking you're going to have to come up with, you're going to have to make a judgment about whether or not the population that you are drawing your sample from, whether or not it's normal to begin with, or approximately normal. That will make a determination on whether or not you can say if your sample size is big enough. Okay. So then you're going to write down your numbers. The sampling model for sample means is approximately normal. Okay. And notice we're using the notation for a random variable. The expected. Notice that. Capital italic E. The expected value of Y bar is 143.7. Okay. Now, we have a standard deviation, 3.64. So we're just simply going to we'll calculate a z-score. Z equals Y bar minus mu over sigma divided by the square root of n. Okay, we're using the sampling distribution for y bar after proving that we could do that. The sampling distribution is based on the normal model. Okay, so z will equal is going to equal 143.7 minus 1. I'm sorry. I'm doing the wrong thing here. 140 minus 143.7 over the standard deviation 3.64, which they went ahead and calculated. In other words, it's the standard deviation divided by the square root of n. And so the z, now you can see just using your basic math sense here, the z is approximately equal to 1. It's slightly less than 1. Okay, let's go ahead and use the calculator here. Let me get this over here. So I'll clear this. So 140 minus 143.7. Should be able to do that in my head, but I'm not up to it, I guess. Divided by 3.64. Yeah, okay. So, I'm sorry, approximately -1. My mistake. Okay. So, well, that's not unusual. It's only one standard deviation away from the mean. So, no. According to the 6895 99.7 rule, suggests that the reported mean of 140. Now, this is the conclusion. You got to write all this stuff out. Okay. By the way, notice you went to the preconditions and then your transition sentence. The sampling model for sampling means is approximately normal. Okay, with the mean is 143.7 and the standard deviation. That's an important, necessary, absolutely necessary thing to have. Okay, we have another step-by-step example, and more information from the CDC, our favorite purveyor of population parameters. And again, what's on the left is what you do, and what's on the right is what you produce. Okay? Left is what you do, think, show, and tell to yourself. And then you are going to, and on the right is what you must produce. Okay. So let's get into this. All right, so the CDC, mean weight of adult men in the United States. Okay, adult men U.S., okay? So that's our population. Adult U.S. males. Mu, population parameter, equals 190, and sigma equals 59 lbs. This is lbs. Okay. All right. An elevator in our building has a weight of 10 persons or 2,500 pounds. Okay. What's the probability that if 10 men get on the elevator, they will overload its weight limit? Okay. So we've got an n that equals 10. Now, you can see right away that our question, the probability that the total weight of the sample of 10 men exceeds 2,500 pounds is equivalent to asking that the probability that their mean weight is greater than 250, right? Okay. So that puts it pretty clearly. All right, so let's move on. All right. Independence. It's reasonable to think. Now, you're thinking, you're showing you're thinking. Is it independent or not? Okay, we're hoping that the offensive line for Texas Tech University is not getting on the elevator or whatever. Okay, so that would not be a random sample. That would also, not probably be a successful elevator trip. if the limit really is 2,500 pounds. But you got to show your thinking. It's reasonable to think that the weights of 10 randomly sampled men will be independent of each other. Okay, and then I throw in the exceptions here. Randomization. I will assume that the 10 men getting on the elevator are a random sample from the population. So you just can't check that off. You can't blow it off. You must state your thinking in complete sentences, and the thinking you must touch on the issues of random and independence. 10% condition. Okay. Obviously, the 10 is less than 10% of all U.S. men. Is it large enough? Okay, more thinking. What do you think about the population of U.S. men? Do you think that their weights are normally distributed? If you do, then the sample of 10 is big enough for you to use the normal model for the sampling distribution of the sample statistic taken from these 10 men. Okay, now you don't have a statistic, but your Y-bar that you're interested in is 250. Is Y-bar going to be 250 or greater? Okay? All right, so let's put our... Now we're going to talk about, well, what's the distribution of this? What's the sampling distribution going to be? Well, it's going to be mu, comma, sigma over the square root of n. Remember, we're doing a distribution for the sample statistic itself, okay, which is we are speculating at 250. So it's going to be 190, comma, 59 divided by the square root of 10. Okay, and they tell us what that is right here, and we may as well just write it down, 18.66. Okay, now you're on, let me go to the next page. Oops, are we finished? That was it. Oh no, here we got more. Okay. Now let's draw a picture. Okay. Now they're using the whole model to do this, but let's, you guys are smart. So here's 190, and here's 250. So how many standard deviations is 250 from 190? Well, you're going to calculate the z-score. Z equals y-bar minus mu over sigma divided by the square root of n, which is going to equal 190 minus 250. That's going to equal 60 divided by 18.66. That's going to be a standard deviation of at least 3. And in fact, they show you there, it's 3.21. So we know that 3.21 is rather unlikely to occur. This darn thing, I'm not used to this new Windows. Okay. So Z is approximately equal to 3.21. So we know the probability of that occurring is 0.0007. So the probability that Z is greater than 3.21, which is the probability that Y bar is greater than 250, is approximately 0.0007. Now, maybe you're not happy with that, especially if you're a hotel that caters. So by the way, let's just go through this thing here, calculating this. Okay, that'd be second VARS, normal CDF, 3.21, comma, 99, and there's our 0.000. You can see it's in scientific notation, but that would be exactly the same as 0.0066, so you could round that to 7. Okay. So the chance that a random collection of 10 men will exceed the elevator's weight limit is only 0.000. 0.0007. So if they are a random sample, but that's a big if, okay? That football team shows up, and it ain't going to be pretty. All right. Next. All right, variation. Okay. This is an important paragraph to read. Now, what it means, we talked about if the sample size gets bigger, then the sampling distribution gets more normal. Okay, that's good news. All right, that means we make the sample bigger. We have a better chance of being able to use the normal model to evaluate our sample and get a pretty good idea of the probability of our sample statistic occurring, assuming that the population parameter is true. Now, but there's a problem, okay? The standard deviation for p hat equals the square root of pq over n. Notice that n is getting square rooted. And the standard deviation for y bar equals sigma divided by the square root of n. Now, I know that you all remember faithfully and lovingly your math classes in which you worked with the square root function. And I'm sure you remember this from our discussions of discrete random variables and the insurance. That was a wonderful thing. But this is what a square root function looks like. And notice that as n increases, okay, you get less and less bang for your buck. Okay, the curve levels off. It still keeps going upward. It never starts going down or whatever. It never gets flat, but it goes up at a lower and lower rate because you're taking square root. Okay, and that's they call that the law of diminishing returns. And you only have so much time and so much money in which to collect your data. And if you want to cut your standard deviation in half, you're going to have to quadruple your sample size. We went through this in the first semester, okay? And to cut it at half again, you need to increase it by 16, and so on. So, so that's part of the when you get into doing statistics and you start reading stuff and reading reports and so on, you're going to see studies done with pretty small sample sizes, and this is one of the reasons why. Okay, now here's an interesting story about Bill Gates and trying to get with smaller schools and everything, and they run into an interesting thing. They thought small schools were high performers, but it turns out that small schools are also the lower performers. Now, this paragraph is very important, drawing the distinction that we've mentioned before, but we're going to talk about it again. The central limit theorem does not describe the distribution of the data in the sample. Now, remember, if you're going to talk about what a sample of proportions looks like, it's just going to be two piles. Let's say this is a histogram. Here's your S's and here's your no's. Okay? Nevertheless, you can end up with a sampling distribution of p hats. So this is the population. Okay? Let's say that it's, 60 in favor and 60% in favor and 40% not. Let's say this is the true population breakdown. Okay? Definitely not a normal looking population. And yet, when you do a distribution of, let's say, 10,000 simulated p hats from this population. So this is the population distribution. Okay? Here's the distribution of the p hats, and they're going to center around p, and they're going to be normal, approximately normal. But each one of those little p hat samples is going to look like this, or some variation on it. They're going to all look, none of them are going to have a normal distribution, the samples themselves. What has a normal distribution? The distribution of the statistics taken from each sample. Okay? Each one of those p-hats is going to distribute normally, whereas the distribution within the samples themselves will be obviously not normal. They can't be because it's binary data. Now, when we talk about, here's a population that's really skewed. Let's say, I don't know what this would be. Income, okay? Let's take income. U.S. family income, okay? Here's math teachers. We're way out here making millions of bucks. Here's everybody else back here, all you losers. Anyway, so here's U.S. family income. Now, if you take a large enough sample, here's sample 1, okay? Sample 1. And it looks like this. And here's a y-bar from it. Okay, and here's sample 2. And it's going to, let's say it looks a little bit like that. Okay, and here's another y-bar. And here's sample 3. And it's going to look, if it's big enough, it's going to, the distribution of the sample itself is going to look like the population. And here's another y-bar. But if you took all those y-bars and put them into a sample, they have a sampling distribution, the y-bars themselves, that is approximately normal, centered around the true population mean. Okay. And this brings us to just checking. 4, 5, 6, and 7, which is the end of your just checking. This will be due Friday morning, just before the lecture. Lecture's still on. Okay. JC4. Human gestation times, mean of 60 days, standard deviation about 10 days. Record the gestation times in a sample of 100 women. Do we know that a histogram of the times will be modeled? No, we don't. We absolutely don't know that. We know that we have a mean and a standard deviation. We have a couple of nice population parameters. We have no idea of that sample. It probably wouldn't be normal, okay? For one thing, okay, so here's a sample of 100. What does the population as a whole look like? I would be surprised if it was not skewed. We got some people taking, I don't know if it's skewed to the left or the right, but it's not going to be normal. Okay, so 4 is no. Now explain why. Okay, we don't know if the population is normally distributed. So we can't have any idea about the sample. Now you may say, well, what the heck are they doing taking a mean and a standard deviation from a population that's not normally distributed? Well, they did, okay? They did it. And that's going to happen. I know we said we weren't going to do that in the first semester. Now here, people are doing it. Just deal with it, okay? Just get over yourself. Okay, 5. Suppose we look at the average gestation times for a sample of 100 women. If we imagine all the possible random samples of 100 women, which would be billions, we could take and look at the histogram of all the sample means. What shape we have? We've already answered this question before. It would look normal. Okay, approximately normal. With all of our y-bars, y-bar, billions of y-bars in here, all centered around the true mean. And what would be the standard deviation? It would be sigma over the square root. I think I just said, what would the center be? The center would be mu, and the standard deviation would be sigma divided by the square root of n, which would be, okay, so what would the center be? 6. It would be 266. That's what mu is. All these y-bars, as long as they're random independent, not too big and not too small, that is representative of the population, are drawn to the true mean, and so their distribution would be centered around mu, approximately normal, according to the 68, 95, 99.7 rule. Okay, so where would be the center of distribution of the histogram? It would be mu, 266. And the standard deviation? Okay, the sigma for y bar would equal sigma over the square root of n, which you can do in your head because it will be 10 divided by the square root of 100, which obviously is 1. Okay, sampling distribution models. Okay, the statistic is a random variable. So now, we've said it, we're saying it again. We can't know what our statistic will be because it comes from a random sample. It's just one instance of something that happened for our particular random sample. A different random sample would have given a different result, okay? The sample-to-sample variability is what generates the sampling distribution, period, okay? The sampling distribution shows the distribution of all possible values the statistic could have had. Okay, we could simulate the distribution by taking lots of samples, by pretending to take lots of samples. But we can use the central limit theorem to always tell us the distribution model for a single sample, which means you don't have to run simulations, you don't have to take 10 billion samples. You can take one sample and know what its relationship is going to be to the population. Sampling distributions arise because samples vary. Okay, now, I already went through this before with my little example. We're going to do it again. Here is a population, okay? Described here, and here's the standard, here's the mean right here. Here's mu and sigma. Now, here are 3 samples. Now, notice there's a histogram, picture of the sample, the distribution of the sample itself. And they're all skewed. Okay, none of them are normal. But they all yield y bar 1, y bar 2, y bar 3, and they all go into making the sampling distribution, the distribution of the y bars, whose standard deviation is sigma divided by the square root of n, and that's a normal distribution. What if the population is far from normal? Then you need a larger sample, okay? And they talk about this here, okay? Size 10, size 50, okay? 10, really skewed. This is the sampling distribution, okay? Sampling distribution for size 10 for a really skewed. Let's go back and look at the population again. Super skewed, okay? We're super skewed. Here we are way out here. What is this? This is the compensations of the Fortune 500 CEOs, okay, back in chapter 4. All right, and here's a box plot. Look at these outliers, okay? It's just crazy, crazy skewness, all right? Okay, now, here is a sampling distribution of a bunch of y bars. They simulated 1,000 samples. This is 1,000 sample, 1,000 y bars here, size 10. It's skewed, so it does not have a normal distribution. We could not use the sampling distribution, the central limit theorem, to describe the distribution of those samples. Now, here's size 50, still not normal, can't use the central limit theorem. Okay, size 100, okay, still skewed, we would not want to use a normal model. We have to get to size 200 for something that skewed before we can use the central limit theorem and the normal model, the 68, 95, 99.7, normal CDF, all that stuff, to figure out the sampling distribution for a particular sample taken from this population. Okay? All right. So that's something to be aware of. And I would tell you that these pictures take some study. If it's extremely skewed, then you're going to need a sample size in the 200s, okay? What can go wrong? Number 1, don't confuse the sampling distribution with the distribution of the sample, which we just talked about and which we will reiterate right here, okay? Here are distributions of samples, all skewed, okay? Taken from a skewed population, so you expect the distribution of the sample itself to be skewed. But the sample statistics, considered to be a random variable, okay, y bar 1, y bar 2, y bar 3, themselves have an approximately normal distribution around mu with a standard deviation of sigma divided by the square root of n. Okay, back to what can go wrong. All right. All right. Secondly, beware of observations that are not independent. Okay, we talked about the elevator riders, all right? Good sampling practice and well-designed randomized experiments ensure independence. They are also extremely difficult to ensure, okay? Just know this, okay? Now, you're going to make all kinds of, you're going to say, well, I think it's independent, I'm done, whatever. But know in your heart of hearts that random independent ain't easy. Only comes after a lot of work. Okay, but we're not going to get into all that work now. Watch out for small samples from skewed populations. Okay, kind of already said that. What have we learned? The central limit theorem tells us that the sampling distributions of both the sample proportion and the sample mean are approximately normal for large enough samples. You must remember this, and it's not that hard to remember. But get it into your head now and don't let go of it. We are going to use it a whole rest of the year. We've learned that usually the mean of a sampling distribution is the value of the parameter estimated. Okay, for sampling distribution, okay, so is P and mu. We learned about the standard deviation of a sampling distribution. Okay, we've been through all of this. Next page. We learned about the central limit theorem, the most important theorem in statistics. Well, for right now, I'm sure there's more important things, but I don't know what they are. And sampling distribution of a sample's mean tends towards normal, no matter what the underlying distribution of the data is. The central limit theorem says that this happens in the limit as the sample size grows. The normal model applies sooner when sampling from a unimodal symmetric population and more gradually when the population is very non-normal. Vocabulary, sampling distribution. All of these, see these 1, 2, 3, 4, 6. That's all you got, 6 terms. That's it. I don't think there's any on the next page. Now we start the homework. Okay. Different random samples give different values for a statistic. The distribution of the statistics over all possible samples is called the sampling distribution. The sampling distribution model shows the behavior of the statistic over all the possible samples for the same size. Now, I can read the rest of this to you. Let me read this over. Okay, sampling variability. All of this, you've got to know this. Central limit theorem, we've been over that. Sampling distribution model for a sampling mean. Okay, so you got proportions and means. You got to know the difference. All right, that's it. You're liable for the rest of the homework. Due Friday morning. Turn it in to the box at the back when you walk in the room, and then sit down and get ready for the lecture, for the guest lecture.